Bismillahirrahmanirrahim and Assalamu alaikum dear students. Bismillahirrahmanirrahim and Assalamu alaikum dear students. Welcome to our next lecture. This is the last part of our chapter, that chapter 4 that we have been looking at in the previous lectures. Today we will look at that how from different models, what is the criteria that would allow us that which model should be selected for the best performance. Previously we have seen that as the complexity of the model increases, the fitting process gets fine-tuned. If the complexity of the model is smaller, it may underfit. For higher complexity it may best fit, and for more higher complexity it may overfit. There are a number of procedures that we can use to fine-tune the model complexity. First one is called the cross-validation that we have discussed in the previous lecture. In cross-validations, actually we cannot calculate the bias and the variance of a model, but we can calculate the total error, right? This is a complex procedure, so we just calculate the total error. A training set increases the model complexity, decreases the training error. It's an interesting point that we have already seen, that as we make our model more and more complex, the training error reduces. However, the validation error may increase. Error on validation set decreases to an extent, then stop decreasing and or start increasing if there is noise in the data. For example, we can see that as we have seen in the previous lectures, with the model complexity the training error reduces, right? This is the model complexity along the x-axis, and this blue line is shown for the training data set. However, if we have the validation data set, the error reduces up to some extent and then it starts increasing. So this is the optimal point, which is basically the good fit point. In real life, we cannot calculate the bias and estimate it using validation error. However, validation error also contains the variance of noise, right? Because if there is the noise in data, so this validation error that we calculate, which is shown here in the golden line, that also contains noise. It means that this measure is not accurate. The first approach, which is a cross validation, that is given like this. Let we have the training data set which consists of, for example, 100 instances. Each we make splits of 20 instances each, making 5 splits for the 100 instance data set. We take one instance or one split or one fold for the validation, whereas we train our model on the remaining data set. Similarly, for the next experiment, we take the next part, this next 20 part for the validation, and we take all these white parts for the training and get the results, the predictions or the regression. Similarly, the third experiment, where we take the third split or third fold as our validation and others for the training. Similarly, the experiment 4 and the experiment 5. We call them as 5-fold experiment. Here you can see that we can either use the same estimator G1x for each experiment, for experiment 1, experiment 2, experiment 3, 4 and 5, or we can take different training sets, different estimators, and we can take the average of those. So this is known as cross validation. Try to understand the process, right? We train our data and then we test on the validation set which is not used in the training, and we use different estimators. For example, 5 estimators we are using here to find the predictions, and then we take the average of them. This we have discussed in the previous lecture as well. And even we can have the same estimator for 5 cross validation, and we predict the results on that, and then we take the average to have the best estimate. Model selection procedure, another technique. Now look at that, the error that we define could be written as this. The error which is produced with the data set that we have, and then we have some error which is introduced when we increase the model complexity, and that is given by delta, which is multiplied by lambda. An augmented error function is used. We call it as an augmented error function. We penalize the complex models with large variance using this lambda. Now keep this point in mind. The models which have the large variance mean the models which are more complex, we penalize their outputs with this factor. Large value of this lambda favors simple models and bias may be introduced. Again, when we penalize the large models, so this is actually an effort to convert the complex models into the simplest models, or we suppress the complex models to behave like the simpler models. And we have already seen in the previous lecture that simpler model have higher bias, lower variance and higher bias. This lambda is optimized using cross validation, which we have seen in the previous slide. First term in equation is training error. In this equation, we see that the first term, which is given this error on the training data set, it is the training error. And the second is an optimism term estimating the discrepancy between the training and the test error. Right? Basically, we are using this term to penalize the performance of our model and suppress them and to change them or to force them to behave like the simpler models. There are methods such as a Koike information criteria, which is considered as AIC, or Bayesian information criteria, BIC, work by estimating this optimism and adding it to the training error to estimate the test error without need of validation. It means that we can use these methods, these Bayesian AIC or BIC, to estimate this term and introduce it here, right? So regularization is another technique to change the performance of complex models like the simplest models. For example, if we look at this slide, we can see that we have the green line and we have the blue line. The green line is given by this equation, which is comparatively more complex. We normalize it, we regularize it in order to get the better fit, where we reduce the variance of our model. So here you can see that how it has been done. It's a simple concept to understand. Regularization, the magnitude of the second term, this one, it increases linearly with the number of inputs or features, input features. As we increase the number of features, this model complexity increases, right? Because more the features, for example, if we have one feature, so we may have, this is something like this, y is equal to w1 x1 plus w0. However, if we have two features, then y would be changed like this, w2 x2 plus w1 x1 plus w0, if this is the linear model. And in case of non-linear model, even that may be changed like this, w1 x and w2 x2 square. So it would be a quadratic formula. It means that as we increase the number of features, the complexity of our model gets increased, and this term also increases. The complexity of the model increases, so this term increases. And it decreases with increase in the training set size. As we increase the set size, this model complexity decreases because it becomes more and more general, right? For example, if we have only two instances, one is here and one is here, so our model, for example, it may be something like this. But if we have three inputs, one is here and other is here, so it could be like this. If we have four inputs, one is here, and other is here, so it may something like that. right? So generalization increases with the number of instances in the data set. Try to understand this concept, right? And the magnitude of second term increases with the variance as noise is added with sigma square, right? Model complexity increases, variance increases, we already know. So this term increases. Variance of noise can be estimated from the error of low bias model. So we can use error of low bias model as well, which is a simple one basically. Model complexity measure. How we measure the model complexity? There are two ways. Number one, number of independent variables in the model that we have to find. For example, how many features are there, it tells us the complexity of the model. More the number of features, more the model is complex. And then another thing that we have seen, which is the VC dimension or Vepnik-Chevroninsky dimension that we have seen in the earlier lectures, is another measure for the model complexity. Structural risk minimization. This uses a set of models ordered in terms of their complexities. In cross validation, we have seen that we can use one or multiple models to estimate the predictions, right, to find the predictions. So we arrange multiple models in the form of increasing order of their complexity. And set of decreasing lambda i's is used to get a set of models ordered in increasing complexity, right? So we use this normalization factor to make their arrangement proper and to bring and to make their variance smaller. Model selection by SRM, structural risk minimization, then correspond to finding the model simplest in terms of order and best in terms of empirical error on the data. Empirical mean training, right? So try to understand that how structural risk minimization could be used to find the best model. And here you can see that this is the training error, which is empirical error, and this is the generalization error or the validation error. Take underfitting to overfitting, and somewhere we find the best point. Model selection procedure. Another technique that we can use for this is the minimum description length. It is a description length based on an information theoretic measure. What is that? We look at here now. Kolmogorov complexity of a data set is defined as the shortest description of the data. How we find the shortest description? If the data is simple, it has a short complexity. It's very interesting. If the data is simple, we know that the complexity is smaller. For a sequence of zeros, we can just write 0 and the length of sequence. For example, if there are 3 zeros in our data set, we can replace them with 0 and find to make its representation smaller, minimum description length basically. Right. If data is completely random, we cannot have any description of the data shorter than the data itself. It is obvious. If a model is appropriate for the data, then it has good fit to the data. Model description can be used instead of data. That's very interesting. If we have reduced the data into smaller form, then we can use simpler models to perform the predictions on this data. Try to understand it again. If the number of features are higher, model would be more complex. And if we can reduce the number of features by using any technique, it means that we can apply the simpler models. We want simplest model describing the data. There is a trade-off between the model complexity and interpretability. This we already know that as the model gets complex and complex, it becomes difficult to describe that model. And as the model becomes simpler, it becomes easier to describe it. Bayesian model selection. This model is used when we have some prior knowledge about the appropriate class of approximating functions. This prior knowledge is defined as a prior distribution over models. For example, we know about the models that from which distribution they belong. Given the data and assuming a model, we can calculate this probability given data of the model using Bayes rule, which we have already studied. We are not going into the details of Bayesian selection criteria, however, we are just having the overview of it. We choose the model with the highest posterior probability, right, or take an average over all models weighted by their posterior probabilities. It means that either we can use the maximum posterior or we can take the average and then use it. Taking the log on both sides of this Bayesian formula, which we have seen in the previous slides, we find the log likelihood of the data in training error and then log the prior in the penalty term. So this is the log likelihood and this is the log of the prior. If we use regression model and use the prior with this assumption that P of W such that it belongs to normally distributed data, we minimize the term this is the sum of squares, and here this is the augmented error basically. So we find the augmented error and we try to minimize it. To get smoother fitted polynomial, choose Wi such that these are close to 0 and decrease error. The parameters Wi are the parameters. So parameters must have the minimum value basically as we use them here. So the penalty term helps in smoothing the curve, and we have already seen this in the previous slides where we have saw that we had the green and we had the blue kind of curves. When the prior is chosen such that we give high probability to simpler models, the Bayesian approach, regularization, SRM and MDL are equivalent. Try to understand this point as well. When the prior is chosen such that we give higher probability to the simpler model, mean that we want to select, we have more chance to select the simpler models. Right? Cross validation is different from all other methods for model selection in that it makes no prior assumptions about the model or parameters, and most of the cases we are using the cross validation because it gives better results comparatively. If there is a large enough validation data set, it is the best approach, the cross validation. The other models become useful when the data sample is small. Most of the time you people will be working with the data set which are big in size, so it means that cross validation is more appropriate for you people. This was a short lecture. I hope the concepts given in this lecture are understandable for you. For this, enough for today. I hope you got it. Allah Hafiz.